Welcome everybody to this TAP colloquium. Before I introduce our speaker, there's actually an announcement that I think made, which is about the TAP prize, which was awarded to Yang Kai for the paper. The title is at the bottom: The Dynamics of Ultrarelativistic Charged Particles with Strong Radiation Reaction, which is an Aristotelian equilibrium state, which I don't know what that means personally. So congratulations to Yang Yai, who is now not in Tucson anymore. He moved to Shanghai to be a fellow, but congratulations. Back to the meat of today. So today's speaker is Joonas Nättilä, who is right now in a joint position at Colloquia and professor at the University of Helsinki in Finland, where he actually did his PhD in Finland, not in Helsinki, in Turku. After which Joonas moved to be a postdoctoral fellow at Nättilä in Stockholm, and then he moved to New York. And actually, Joonas is one of the people that convinced me the US as well. We had a talk when he had already decided to move to New York, but was still in Europe, and I was deciding this as well. And then we spent a few years in the same group, broadly speaking, at CCA, although we work on quite different things, but related. And Joonas today is gonna talk about extreme plasma physics, which is his strong expertise, and take it away.
Thank you, everyone. So, yes, today's topic will be this kind of mixed bag of topics on extreme plasmas. So plasma physics is an old field, but now we are basically cranking up everything into an extreme version, meaning higher energies, higher magnetic fields, everything is extreme. And this is something that's happening in space, especially around neutron stars and black holes, that I'm going to introduce to you. And this will be kind of a mixed showcase of what we've been recently learning and kind of being able to accomplish in this field, which is really a young field of only a few years, maybe started from the computational perspective, let's say 10 years ago, when we started to have numerical capabilities to actually do three-dimensional simulations that actually capture these plasma dynamics in the astrophysical context. So it's, I think, an exciting time to be doing this kind of research. And because of the mixed bag content, I'm also very happy to have questions in the middle. So just feel free to stop me, and we can have chats and questions about the particular things about that I'm going to discuss. But without further ado, let's kind of prime ourselves now on the fact that we are in space. And what will be discussing are these two objects that I call compact objects. So to get you kind of primed on the astrophysical side, this is a picture of our own sun. That's the closest star we have. And then sun has a mass of roughly 2 × 10⁻³ grams, radius of 7 × 10⁻10 centimeters. And then surprisingly, when you actually take the mean density of the sun, you end up with something like 1 gram per cubic centimeter. So similar to the water densities. But this is, of course, you have to remember that this is the average density of the system, but still it's not actually that dense of an object, similar to what we have on Earth and water. So what happens in stellar evolution that we've been actually studying for a long time? You have one of the experts here, which is Matthew, that you should ask definitely all the questions about stellar evolution, all that murky details, and I point them to him. But what happens is that if we now take what is called a massive star, so not our own sun, but something like roughly a factor of 10 more massive, you basically let it evolve. What it does is that it burns the material, radiates it away, and eventually it will collapse due to a gravity, because there's no pressure anymore supporting the object, and then the gravity will squeeze it together. And then this will lead up into a so-called core collapse scenario, where we have the outside of the star falling and pushed out. Then they are basically ejected, and then the core, there's some remnant left here in the center of the star that then collapses together into a point. And basically we are left with this kind of a dense core being compressed, and then some kind of a more hazy nebula around the old massive star that we had. So the point here from the physical perspective is that the if you think from the perspective of having an atom, here's an atom, some kind of characteristic size of the electron orbit is maybe something like 10 to the minus 8 centimeters, and then the core size of the protons and the neutrons in the core characteristic size of those is roughly femtometer, so 10 to the minus 13 centimeters. And you can immediately notice that actually there's a huge difference of 10 to the 5 in the size scales between having a proton and then the actual electron orbiting it in a Bohr radius. What that means is that the most of the atoms are actually composed of empty space. So now what happens inside the core of this collapsing star is that we basically have multiple of these atoms in, and then they are somehow being stick together and pushed out by the fact that you have these electrons that prevent them from going in. But now that we have the collapse, which is an immense amount of material being squeezed in, you can basically think that we are now squeezing all the empty material out from inside the atoms. And we can do this kind of a simple algebra and think that what happens when we take a negatively charged electron and push it into the positively charged core. So basically plus minus gives you something zero, which is neutral, which is called a neutron. So basically, in our very rough picture, what happens is that we push all the electrons in the star and we merge them with the protons, and we are left with only neutrons. So as a conclusion, what happens is that what is left behind is this huge clump of neutrons, and hence this is the kind of theoretical formation of how we create neutron stars. So neutron stars themselves are basically born from what I call this ultimate squeeze of squeezing out all that empty space from the atoms, and you're left with basically something with a characteristic radius of roughly 12 kilometers and mass of the original core, which is something like 1.5 solar masses in size. So now we basically have this huge nuclei in there held together by the gravity of the system. So this is how we create neutron stars in astrophysics, extreme objects, by the fact also that when we start to look at the densities inside these stars, so here an x-axis, here to kind of orient you, this is density in the grams per cubic centimeter. So osmium, which is 20 grams per cubic centimeter, sits somewhere here. Osmium is the densest material naturally occurring on Earth. Again, 20 grams per cubic centimeter. That gives us something like atmosphere of the neutron star. This here is showing the pressure axis inside the star. And then what connects these two is so-called equation of state. So the equation of state tells you basically then what is the relation between the density and the pressure. And you can see that actually, theoretically, we know pretty well how the neutron star and the matter behaves. But then all the way and why we've been interested in neutron star for long, just to highlight this to you, is the fact that while we do know how the neutron star diluted layers, diluted meaning that we go maybe all the way up to here, 10 to the 11 grams per cubic centimeter behave, you start to see that when we reach something like 10 to the 15 grams per cubic centimeter, the models that we have start to deviate. And here I saw a blow up of this region, and actually we don't know what is happening inside the core. Hence, there's also uncertainty related to how big neutron stars are. Because when you realize actually that this core, which is from 10 to the 15 grams per cubic centimeter, that's also more dense than that is density higher than what is found inside protons or neutrons. So this whole range of the outer layers of the neutron star is basically maybe 100 meters in height. And the rest of the 12 kilometers is basically set by the unknown core. And hence the big mystery that we are basically one of the big issues now, trying to combine, for example, astrophysics together and using astrophysics to understand the particle physics and nuclear physics on Earth is also understanding how nature creates and what kind of equation of state is inside neutron stars. So to go back to a more astrophysical scenario, give you orders of magnitudes. Like I said, neutron stars are these objects 12 kilometers, maybe 1.5 solar masses. They vary from something like 1 solar masses to 2 solar masses in size, depending on the neighborhood and their history. But interestingly also, for example, if you take the dimensionless ratio, so this is the U is the compactness, for example, introduced in general relativity as one of the dimensionless parameters, which encapsulates and tells you how strongly the star itself is influencing its space-time, you end up with something like a factor of 0.3 or 0.5 as an expansion parameter. Another way to think about this is that the neutron star is maybe roughly 3 times larger than a black hole. So it's just on the basically a brink of becoming a black hole, just slightly bigger than that. So already GR effects are also important. But now we already kind of introduced the concept of neutron stars. You require quantum mechanics because of the whole packing of the lattice. You basically require GR to understand them because they are very dense. They curve the space-time. And then also on top of this, the magnetic fields they are actually the strongest magnets in the universe, with something like 10 to the 8 to 10 to the 15 Gauss, where to give you kind of a comparison, the strongest magnet we've created on Earth is maybe 10 to the 7, and that's been created by an explosion. So then neutron stars are on the minimum 10 times stronger in the magnetic field, and they sustain it actively. And then all the way up to 10 to the 15, which is many, many orders of magnitude higher in the magnetic field. So also extreme magnets. So you have to take that into account also when you're studying them. And then finally, these are small objects. They conserve their angular momentum, and some of them have been measured, for example, to spin all the way up to 700 Hertz per second, meaning that they have millisecond periods when they rotate each other. So in all aspects, extreme objects that we basically want to understand and study. And then, of course, because of that, they are natural laboratories for understanding extreme plasma dynamics. So today, my talk will be mostly focusing on this exteriors of the neutron star. So basically what happens in the magnetosphere of the star itself. I'm not going to go into the details so much about the interior of the star. If you have questions, I'm happy to answer those. So the first step that we can basically do is that let's think how the neutron star can look like. And I think the best example is the one that we have closest to us is our own sun. So this is showing a UV band image time lapse of 2 days. These are beautiful videos by Jean Doran on surface of our own sun, and you can actually see that this is nothing like a boring sphere that just rotates there, but sun has this active magnetosphere that's composed of these magnetic arcades. So these are actually magnetic loops. There's plasma mechanisms heating up the loops, hence making them shine, making them energized, and then you can see that it's also once in a while bubbling and actually evolving dynamically. So they are actually fascinating objects in itself, I mean, stars. And then from here, we can kind of start to extrapolate that it's maybe not so crazy to expect that neutron stars are also some kind of a messy magnetic field structure that is evolving in time and really showing activity like we have, for example, in the sun. So the big difference from the solar case, the sun and the plasma physics therein and around us is typically what I would consider classical plasma physics. What makes the neutron star magnetosphere different is the fact that there's what I call a concept of quantum sparks. So when you have a very hot object like a neutron star, they can reach something like 10 to the 7 kelvins, so 10 million kelvins in temperature. So the characteristic energies, for example, of photons that can come out from the surface of such objects can be gamma rays, which means that the typical energy of such a gamma ray is a 500 kilo electron volts. So what that actually means is that when you compare it even to the rest mass, so this is Einstein's famous formula, mass times the speed of light squared, the rest mass of an electron is 511 keV. So you actually see that the gamma rays that we have in the medium start to be comparable to the electron rest mass, and hence we actually unlock some new quantum strangeness in the system by the fact that now, for example, we can have 2 gamma rays coming together, colliding, and then they produce and turn from photons into a plasma itself. So this basically this quantum electrodynamic QED effects enable the photons radiation to turn into plasma, and also plasma to turn into radiation. So this is something, of course, that doesn't happen in the solar case, but kind of requires this QED treatment of the whole atmosphere, the magnetosphere of the neutron star. So in kind of schematically, this is showing the luminosity of the system. So again, basically how much radiation we have in the system in terms of radiative power. And then in the y-axis, showing some kind of characteristic scale of the system. So what we can think of, another way to think about this quantum spark, or how likely you are for that, is basically how much energy and power you have in a small volume. So typically, when we think about standard plasmas, for example, found in stars, found in fusion reactors, you live in somewhere here on the left top corner, which means that we have low power or then large sizes of the system, so we don't have a lot of energy density in a small volume. But the curious thing is that what we've been able to do and really focusing on recently is that we've been pushing into this new uncharted territory of basically radiative dominated plasmas, where you start to have more and more energy density in radiation, which unlocks on various levels different kind of QED effects and enabling this radiation also to start turning into plasma and plasma into radiation. Then, of course, ultimately, when we end up somewhere here, magnetars are a special form of neutron stars. Then by that time, you can characterize the luminosity with so-called compactness parameter that I'm not going to go into, but if you're interested, you should ask. And then there, for example, this so-called luminosity is already 10 to the 7, which means that these are 10 to the 10 million times more dominated by the radiation than they are by the plasma. So actually the role of kind of plasma and radiation changes completely. So this is kind of what we've been doing from astrophysical side, is we've been pushing from the classical regime, which is already hard, into this new and uncharted territory of radiatively dominated plasmas. So numerically, half of my job is also to do basically simulate this and enable the computational design simulation of these systems, and that's been led by us developing this open source simulation toolkit. This is called Runco, which enables these so-called particle in cell simulations. I'm not going to go into very much detail on the simulation. I know that there are some high performance computing people in the audience, so I'm happy to talk about the kind of technical details. But for example, we are now targeting CPU and GPU accelerated platforms and are able to do very large simulations. We are using modern C++, if you're familiar with those, full 3-level parallelizations. We need big computers to simulate the system that we are doing. And then one of the driving kind of paradigms that we've been pushing on is having an open source software available for everyone to use that we've been developing in. So the code, for example, is available here for everyone in the GitHub repository, and everything you see here is produced with this code. So to give you kind of an introduction onto the method that we use to simulate these diluted collisionless plasmas in the astrophysics, this is done with so-called particle in cell method. The method dates all the way back to the 60s and 50s when this was devised. Of course, back then the computers were very primitive. You could maybe do a maximum of 100 particles to simulate a gas of a plasma. These days we do something like 10 to the 13 particles to actually simulate, and that has been something that has been really changing the field. That from going to simulating 100 particles, we are now going into simulating thousands of billions of particles, which has basically enabled this new results in the field. So how the method works is that if you go to your electrodynamics classes, you remember that we have Maxwell's equations. They both have basically terms that tell you how magnetic and electric fields evolve. So what we do is we evolve those self-consistently. What we do is we sprinkle on top particles, electrons, positrons, charged particles. And then what you have to do is you interpolate the field that is living on a grid to the location of those particles. Particles themselves, they are charged. They obey Lorentz force, meaning that they are accelerated by electric fields and they gyrate on a magnetic field. And then final thing that closes the loop is the fact that when you have a charged particle moving, you already also know from electrodynamics that the charge moving basically induces an electric current that then feeds back here into the Maxwell equation. So we basically close the system, and now we self-consistently simulate these plasmas. The price to pay is, of course, that now we really need to simulate the individual electrons and positrons or electrons and protons in the medium. So this would be equivalent basically of having a fluid dynamic simulation where we simulate the individual molecules and how they collide. And then, of course, if you sprinkle a lot of them into the system, eventually the water starts to behave like a fluid. Same thing here, the plasma starts to behave like a plasma if you have big enough systems. But then really the price to pay is that you need huge computational resources and simulations to do this. The advantage of all of this is really that you are simulating stuff from first principles. So you're not doing approximations on how the plasma behaves. if you see acceleration of the particles or energization, heating, these are all coming from first principle methods. So this is something that really does help us build kind of a confidence on our results, that these are things that emerge self-consistently from the first principles, these primitive laws of Maxwell's electrodynamics and then Lorentz forces. Yeah.
What are some of the, are there commonalities in how when we scale up the number of particles in the cell from 100 all the way up to these billions numbers, different changes in the system that we start noticing that pattern up?
Definitely, first of all, the 100 particles, one of the first particle in cell simulations were 1D, because you couldn't do the 3D spatial dimensions at all. 100 is kind of not enough to give you, for example, statistics on like plasma, for example, wants to thermalize locally, which means that it has a local thermodynamical equilibrium. So we do see Maxwellians forming. But then, for example, 100 particles is not enough to see a Maxwellian really forming, and then deciding that when you have 10 to the 13 particles, yes, you actually start to see that local volumes of the box, tiny cells, are in a thermal equilibrium with the neighbors. But then another thing, of course, that is important is that when you simulate extremely tiny systems, 100 particles, you see the plasma dynamics of the individual particles. Something that really has changed the field is that when you go into big simulations, now you resolve those tiny plasma dynamics that I'm going to discuss actually after this. And then you also resolve the so-called MHD scales, so the magnetohydrodynamics large scales of the system, where you start to have collective phenomena. So that transition is what basically really changes the behavior of the system, from simulating microphysics to simulating mesoscales. Sam has a question.
What's the mechanism for thermalization, and what sets the temperature in these?
That's an excellent question, because these are collisionless plasmas. So how can you thermalize by not having collisions? By definition, you can see that we don't collide any particles. So the thermalization mechanism is that what has been known in the plasma simulations and in realistic plasmas that we observe on Earth, that there are actually effective collisions between the communicated by the electrodynamic fields. So, for example, when your particle flies next to each other, they radiate electromagnetic waves and excite them, and then the neighboring particle feels that waves, and actually that's how they talk to each other. So it's kind of an effective collision. That
you resolve those waves in PIC simulations?
Yeah, and for example, we see one of the biggest problems is the heating of the system, because we are artificially increasing the heating by simulating smaller systems than they are. So that is a known phenomena, that you actually do see the heating coming from the individual particle motions. So, like I said, this has been the kind of de facto methods from the 60s, and now what we've been pushing really and doing this heroic act of really putting in also the quantum electrodynamic effects in. This has been something we've been doing in the recent years, in the recent last few years. And what we basically have done is that on top of the electrons and positrons, we've been now starting to introduce also photons into the medium, and then unlocking basically the quantumness of the system by, for example, adding into the whole loop, let's say, Compton scattering, which is how electrons and photons talk to each other, or for example, synchrotron, which means that there's an electron or a positron and it emits a photon, and then there are these all self-consistent reactions. You basically have to dig into the quantum electrodynamic books, look up the differential cross sections, all of these processes, and then simulate with the Monte Carlo way the scattering between these particles. So in this case, like what Sam was asking, these are real scatterings between the different particles. So to highlight the most important ones that I'm going to focus on this talk is Compton scattering. So that basically means is that we have a photon and an electron scattering and exchanging energy. That's the kind of the basic default. This is showing the Feynman diagram of that. Actually, all of the lowest order quantum electrodynamic effects are kind of the variants of the same Feynman diagram. So you can just watch from different angles, and you end up with the by symmetry with the different lowest order operations. So another one is pair annihilation, which means that if we have an electron and a positron coming together, they can annihilate, and because of the conservation of momentum and energy, they have to emit two photons out from the system. And vice versa, there's a mechanism called photon annihilation, where two gamma ray photons, if they have enough energy, collide and then produce an electron positron pair. So these are the lowest order effects you can have. Then you have many much more complicated effects like 2 to 3 and 3 to 3 effects that are then higher order expansions of the QED theory. But what we really did, and I'm not going to go into detail here, is that we went into and implemented all of this exactly with the exact differential cross sections in order to simulate these processes from first principles again. So the first application that
So I'm curious, what sets the length resolution of the simulation? Is that the Compton wavelength or the gyration radius or something else?
That's a good question. Like from the plasma dynamics point of view, what sets the resolution is that you have to resolve so-called plasma skin depth, which is the smaller scales that you can kind of have holes in the vacuum gaps in the plasma. Beyond that, then you basically transition into microphysical scales. So that already sets you some minimal scale. Another way to think about that is that vanilla peak simulations, they have to resolve the small scales, meaning that the interactions between the electrons. But then, of course, radiation also sets you another scales. And for example, not only you have to resolve those interactions from the plasma perspective, but you, for example, also have to have enough resolution in the momentum space to resolve like statistically, for example, the equilibrium between all of these systems. So you also have some constraints on how many particles you need locally in order to reach global equilibrium. But there's a third one is, of course, the kind of the cross section of the interactions, which you were, I think, alluding to by saying that there's a Compton wavelength also in the system. But that you can think of that basically sets the rate of how often these interactions occur. So that's kind of a dimensionless parameter that we can vary in the system. And I'm going to actually discuss the implications of that recently.
I may not be able to understand this correctly, but it seems that the electrodynamics is still being treated classically in the system.
Yes.
QED and results from QED are being added as a prescription.
Yeah, that's true. That's true.
I'm wondering how good this approximation is, and curious if you won't you have to treat the electrodynamics itself in a quantum framework?
Ultimately, there are some cases like magnetars, for example, where eventually maybe that is needed. It's not actually clear at the moment. This is kind of, I think the estimates are that it's borderline important. Most of the time, the scales that the plasmas evolve actually the plasmas are diluted, so the typical mean free length scales between interactions is actually long, which kind of helps you out from the quantum scales. The problem is that, like you said, that we are kind of mixing quantum scales by QED and then the larger plasma scales, which are still tiny. But it's definitely, I would say that in classical extreme systems like pulsars, black holes that I'm going to discuss, this is not important. Maybe in the case of, for example, magnetars, that is because, for example, the strong magnetic field also makes the electrodynamics nonlinear, if you're familiar with this. That is definitely yet another battle that we have to fight at some point. Not today. So the first application that I want to highlight is two neutron stars colliding, and something we've been thinking about is that whether you can somehow basically get some kind of a signal out before two neutron stars. So neutron stars are living in space. Sometimes they come in pairs. They are colliding together eventually by losing energy with gravitational waves. This was the big discovery of LIGO and Virgo, where we detected two neutron stars in 2017 to collide, and we really measured the gravitational waves coming out from them. And something we've been thinking lately is that could you also get X-ray precursors before the merger happens out from these systems? And it's actually quite natural to think that when we have two neutron stars, they have their own magnetic fields inside of them, and when you start to push them and they start to spiral in together, at some point the magnetic field starts to interact and it turns into an extreme plasma problem that we want to understand. So this is kind of the background from the first problem that we've been thinking about. And from the kind of more schematically, what you can think is that then, for example, we can have two neutron stars. They have some orbital separation. The system is orbiting, and we've identified two different regions that can be energized in these systems. So the first one is that if you have a magnetic moments of the stars pointing anti-aligned, that means that I can have magnetic field lines that actually go like this, and they connect all the way back to the different star, and basically it's a joint magnetosphere of the star that when you put them close enough. And then there are these regions where you actually have an opposing magnetic field lines, which are prone to so-called magnetic reconnection plasma instability. So this is one possible way of basically getting magnetic flaring type of activity from these systems. Another one is much more kind of naive. You can also see immediately whether it's irrespective of the orientation of the magnetic moments, is that when you push the magnetic fields together, there will always be also a shear layer in between the systems here. And actually this also turns out to be an important energization zone for these systems. And then the questions that we've been trying to understand is that, is this enough actual energy and power release so that we could observe some of it? And then, for example, before even that, what is the expected energy band that we could detect some kind of a signal coming from these two cases? This is, of course, one of the holy grails of the whole multi-messenger astronomy, that we would be able to detect, for example, a X-ray signal before the merger. Then we would detect a gravitational wave signal. Maybe then after that, we would detect a kilonova in optical, and really seeing the different neutron star merger alive from pre to current and to post-merger scenarios. So one of the constituents of these systems is that there are, again, plasma effects occurring. For example, when we have these magnetospheres, it's quite natural that this shear interface, for example, excites waves on the magnetic field lines. So now if you do a naive analysis and I put a magnetic field line string and I put two magnetic field waves on it, and I make it so that one is polarized along this direction, another one is polarized this direction, which means that they're linearly polarized. From the top, they look like this, like a cross. And then if you do an analysis from, for example, from the MSD system, you would end up by saying that these do not couple and the waves just pass through each other. So what we did is that we simulated this system. We put in this kind of tall box. Here, this is showing the electric current in the system, and that is basically a proxy of the location of the waves. So we start with this kind of setup that looks in the electric current like this. So two different waves, one going down, another going up and colliding. And like I said, from the linear analysis, you would not expect anything to happen. But then actually what we do very quickly see happens with these simulations is that you can see that the waves start to actually interact non-linearly. And this is something that has been also devised, for example, from 2010 in classical MHD, magnetohydrodynamics, as one of the kind of building blocks of building turbulence in the medium. So turbulence, one way to think about that is basically taking large-scale waves and then being able to create smaller and smaller waves in the system and basically populating and generating this chaotical motion in the field lines. So this was kind of first principle demonstration that the effect really happens. Here, for example, this was the box seems small, but it was 10 to the 13 particles and then close to 10,000 cubed in size. So this was really one of the big simulations we've done so far. And then with this, we were able to demonstrate that when you start with these large MHD scale waves, you can see, especially from the top, that the wave starts to be like kneaded into these smaller and smaller scale ripples. And then those ripples are basically the turbulence. And then they continue all the way up to the microphysical scales of the system. So now you can see when the movie started, we take the wave, we fold it once, now we fold it here twice, then we start to fold it thrice and quadruple and so on until basically we go on and on until we hit the microphysical scales. And like I said, linear analysis would tell you that nothing happens. But then when you go to the nonlinear order or you simulate the system from first principles, you can actually see that the waves do talk to each other. So this, for example, is one of the leading mechanisms that can energize the magnetospheres of these systems. So then we've been doing, for example, here a analysis of what kind of radiative signals you could get from this kind of heating. And I'm not going to go into very much detail of this, but what you can see is that this is in x-axis is the energy of the radiation you expect, and here is the luminosity. And in most cases, irrespective of different model parameters that we put in, sizes, geometries, how much power, what is the magnetic field strength, the spectra seems to be kind of solid in saying that the peak is somewhere around 100 keV, meaning that you would get hard X-rays out from these systems if this happens. So of course, this can be then later on used, for example, to constrain the possibility of detecting, if you do detect 100 keV X-rays coming on before the neutron star merger, then this kind of the smoking gun saying that there's these plasma mechanisms happening in the system. And I'm not going to go into detail of varying different parameters, but it's actually quite robustly saying that irrespective of what you pick, you end up with a 100 keV radiation. Yeah.
Just at the level of order of magnitude, how do these luminosities compare to the sensitivities of X-ray telescopes?
That's an excellent question. So at the moment, we deduced that the best way to detect this is with, for example, with Swift telescope, or then Fermi GPM, which are the most sensitive hard X-ray detectors. And, unfortunately, they are also the only ones that can actually detect 100 keV. They are on the borderline of the kind of sensitivity if the merger happens very close to us, if you have a magnetic field of a 10 to the 12 Gauss, which is a typical radial pulsar strength. Basically, what we deduced in the paper currently is that if you want to detect this into a higher distances, that we typically mean you need something like 10 to the 14 Gauss magnetic field strengths, which would mean that magnetars need to be colliding. That's of course question that you then should direct, for example, the material that can we have from stellar evolution magnetars. I don't think anyone knows, but it's an interesting again constraint that if we do see this, and depending on how bright they are, that would basically directly imply that you probably have a magnetar colliding.
So I make sure I understand. So the effect here would be that as they get close enough together, that
The shear layer.
that the shear layer develops, you're just going to have heating at that interface that glows in X-rays brighter and brighter and brighter.
Exactly.
So it's going to be like just a ramp
Exactly.
up until merger?
Exactly. Right? Lasting maybe for 1 minute before the merger, or a few seconds before, because also at some point the star starts to collide and then they populate the shear layer and basically mask it out so that you don't get any radiation out. So we expect basically something of before 1 minute, like you described, and then peaking up in the peak luminosity zone here, and then going dim, and then we detect the gravitational waves. Still hypothetical, has not been seen, but
well, there have been X-ray precursors. I guess maybe I can ask at the end if this compares to the potential candidates people have seen previously.
Yeah. So next step. This is not a broken slide, but what we are doing is that we are looking into a black hole. So, so another problem that I wanted to discuss before questions is that now let's forget the neutron stars, but actually focus on what I call a solar mass or stellar mass black holes. So actually, interestingly, if you just do the back of an envelope estimates of the typical stellar mass black holes, they are roughly a 10 solar masses in size on the order of magnitude. And actually the characteristic radius of the horizon is something like 13 kilometers. So they're actually bigger than the neutron star, even though they are more compact. Of course, the fact is that they're also more heavy than the neutron star. So roughly I tried to draw them here in the scale. So when we are discussing the neutron star magnetosphere activities, we were thinking of stuff happening here on the close to the neutron stars, for example, when they were merging. But also then we have these big black holes that can also house extreme plasma dynamics around them. So most of these that we detect and have been historically detecting come from X-ray binary. So there we have a black hole and a regular star that is then Roche-lobe overflowing and transferring material slowly in so-called accretion disk into the black hole. And here I'm depicted this schematically by basically looking at the side of the accretion disk. So material is flowing from here sometime outside and then spiraling in like this to the black hole. And what we basically know from equipartition estimates is that this accretion flow also has to carry some kind of magnetic field line, and it's actually surprisingly strong, something like 10 to the 6 Gauss if you expect a dynamo process, for example, happening in the disk. So then we basically bring in material and also this kind of magnetized corona into the magnetic field into the black hole, and we are asking questions that how does that, for example, influence what we observe from these systems. So actually, this states the model, the picture that I'm going to discuss dates all the way back to the Galev on 1979, where he basically proposed that now here, if you have a black hole, we might have some kind of an accretion flow around it and the material spirals in. So this flow also carries magnetic field lines, this kind of magnetic bundles that you can think of almost as a collection of magnetic field lines. And then what happens is that since this flow is spiraling in, you're basically distorting the foot points of these systems. And a mechanism happens that you're, for example, familiar with your garden hose. If you have a garden hose and you keep on twisting from one end, what basically happens at some point is that the helicity is conserved. So you're transferring local twist of the hose into a global coiling of the medium and conserve helicity in the process. So what basically happens also here, if I twist and twist one of the field lines, this starts to create this large-scale global coiling of the magnetic field line. So again, you can ask, is this crazy? Let's look at the sun. Actually, here you can see one of these coils, and if we wait a bit, you can start to see that there's something happening on the surface. So at the moment we are twisting the coil, and actually you see that from our own sun, that something happens and the whole coil bundle coils and then snaps out and then energizes the plasma, creating this halo of UV radiation. So again, something like this phenomena is something we observe on our own sun. Just to play this again, so now maybe you know where to expect them to look. So the coil is somewhere here. I've been twisting it from here. I twist and twist, and at some point it basically flips like the garden hose and then releases all of the energy that there is, launching for also at the same time plasma into the outer space and then energizing this region with heat. So as an idea, it's not so crazy actually to believe that this would happen also in this scenario of having magnetic field lines around the black holes. So what happens in this medium is actually that these kind of systems are composed of two different types of a coiling of magnetic field lines like this. And you know from, again, basic electrodynamics, if you have a coiled magnetic field line, it carries an electric current. Electric current of the same direction means that Biot-Savart law says that these two attract each other. When you put them oppositely signed, they actually repel each other. So when we do a simulation here, this is showing a slice of the density of the plasma, and I start to twist the system. You can quickly see that I form this kind of looking from the top, these kind of bundles of magnetic field lines. Some of them are attracting each other, some of them are actually repelling each other, and then this way quickly leads to a turbulent medium being energized in the system. So again, we kind of ended up with turbulence in the plasma, which seems to be kind of inevitable. And turbulence, why it's nice, is of course that it energizes plasmas and makes them shine. So what I'm thinking about, and I really simulating, is in this kind of a mesoscale box somewhere here on the accretion flow, and you can now see in 3D the same thing happening. When I start and I start to twist these coils, you can see that the plasma density here very quickly starts to form and corrugate and become this kind of turbulent mess that then ultimately energizes also and enables the energy transfer from the magnetic field onto the plasma itself. So one of the key points that we did with these simulations is that now you remember that we also had the QED effects in, and this is showing the plasma density, for example, from a time snapshot of these simulations. And the interesting thing is that these systems, even in the black hole case, actually start to be so luminous that the pair creation and annihilations are important locally in the system. So actually, if I pump energy into the system, it self-consistently starts to create plasma and creates enough plasma, like I showed on the previous slide, that then relaxes into some kind of a quasi-turbulent steady state. The nice thing about this is, of course, that the only then parameter that I put in is how much power I pump into the medium, and then the medium itself, via QED, creates me enough plasma that it wants to be in an equilibrium. And from the kind of radiative perspective, that means that I set some kind of optical depth self-consistently also in the system, which is of course nice, because then we have few more parameters to actually model in these systems, since the plasma density is self-consistently created. Now, another important point here, I said that everything typically tends to become turbulence. Turbulence, something we also know, is actually classically intermittent. This is known from hydrodynamical turbulence, but also now that we start to have more and more inclinations on what kind of intermittency is happening in magnetohydrodynamics. And you can see that when I actually don't plot the density, but I plot the electric current, you see that the electric current tends to form this kind of what I call intermittent structures, which are larger than they should be, and then they tend to form these sheet-like structures in the medium. So these sheet-like structures actually come to play when we have these flux tubes, and when they are pushed together, there is this kind of two-dimensional surface of electric current forming in between them, and then that is also prone to another plasma instability that then actually splits and creates smaller bundles. Then now can split together, and you can actually see the signs, for example, of these smaller scale bundles here. For example, this one is now being corrugated and tearing in the simulation box with this. So you can see this effect better from a high resolution 2D simulation. here I'm showing this box from the top, and you can see that we start to create same kind of a magnetic blobs, islands, but now since in 2D we can go to very high resolutions, you can quickly see that we create these massive bundles, but then in between we create these thin current sheet slices. And for example, here those slices tend to create more tiny flux ropes, and then when they collide, they actually create more tiny flux ropes in between them. And for example, now with 64,000 squared simulations, we can simulate, for example, 3 generations of this process happening. So this is kind of the intermittency of the plasma really at play. So as a final point, I'm not going to go anymore into the details of this, but what I only mention here is that of course, since we now also have photons in the medium, and then what we can do is that we can track also the photons that escape from the system. And for example, in this case, Comptonization, so Compton scatterings, Compton was the electron and photons colliding, allows basically also the energizing locally the photon gas in the system. And what comes out is some kind of radiative spectra. So this is showing the X-rays, and these bands are showing what I get out from the simulations. And then the crosses here are showing for example, observations from one of the black hole binaries, Joonas X1, that has been detected for 20 years. And then known to, for example, have some kind of accretion disks. So this for the specialist is a new plot showing the luminosity coming out. And you can actually see that, interestingly, depending on different parameters that we put in these turbulent boxes, start to self-consistently reproduce these data observations that we have of black hole accretion disks. So it is kind of the first principle demonstration that if you take a turbulent blob of the corona, you make it turbulent, it creates its own plasma and radiation, and then what you get out is kind of naturally, without fine-tuning, what we observe. So I think this is kind of spectacular already from the point of view that I don't fine-tune any of the parameters. It's really the nature, the QED, that decides these radiation spectra out. So I'm going to finish here with my conclusions and future outlook of these systems. So like I hopefully kind of tried to convey to you, neutron stars and black holes are these extreme laboratories of plasmas that we have extremely strong magnetic field lines, makes everything exciting. We have lots of energy to put into radiation. And then from the numerical perspective, of course, plasma dynamics is non-linear. You saw that from the interaction, for example, of the waves. So one shouldn't do only the linear analysis, but there are many murky things like hidden in the non-linearities of the system. One way to of course, study this is then by first principle numerical simulations. And then it is really now in the last few years that we started to have the computational capability to simulate big enough systems that are actually like meaningful to study this phenomena. But then something that I didn't go very much into, and now is of course the computational aspect. So the computational landscape is also changing. So for example, if you look at the historical macroprocessor data, you can see that the number of transistors always went up, but then at some point we started to plateau, for example, with the single core performance. So there are, I think, many challenges ahead also from the computational side in order to be harnessing the Moore's law and going into larger and larger simulations. But I believe that it is with these open source simulation toolkits that we actually start to enable that and enable the whole community to do this. So that's kind of the leading goals of our group in Helsinki, and that's what we strive for. And I'll stop here and thank you.
Questions already, but we still have some time. And also I wanted to highlight we still have 2 spots for dinner if anyone is interested.